So let's review some things about rational functions, including some transformations and some asymptotes. So remember that the denominator of a rational function is the inside transformations. So this says x minus 2, which means that it is going right 2, which means that my vertical asymptote is at x equals 2. That, of course, is because this is my parent function, which looks like this, and had a vertical asymptote on the axes. This outside piece tells me that I move up 4. It's my vertical shift, which means that my horizontal asymptote is going to be at y equals 4. Because my horizontal asymptote was also on the axes in the parent function, and it has moved up. So then there are no other stretches, reflections, or any other transformations. I'm going to plot my 2 anchor points and sketch my rational function. So it's easy to identify our vertical asymptote and our horizontal asymptote when our function is in the form y equals 1 over x minus a plus b, or y equals a over x minus b plus c. So if those are the format that you're seeing your function in, your asymptotes are easy to identify. But what I hope you do notice is that your vertical asymptote comes from the denominator. So let's take a look at some others. Our vertical asymptote here, although I may not know a stretch or a shrink or a reflection or a shift up and down, I do know that my denominator is going to be x equals -2 for my vertical asymptote. For the next one, I have a binomial, but it's a squared binomial or a quadratic, which means I would need to factor this into x plus 3, x minus 3. And I would have 2 vertical asymptotes, one at x equals 3 and one at x equals -3. So yes, in a rational function, you can now have more than one vertical asymptote. So your notes for finding a vertical asymptote are to determine the values that make the expression undefined. So you are going to set the denominator equal to 0 and solve. So those are your vertical asymptotes. So the next part of this worksheet, I'd like you to take a few minutes to pause the video, complete the first 3 columns. So not this one, but I want you to do this one, and this one, and then hit play. I'm going to walk through it a little bit and you can check your work. And then we'll talk about how these are related to the equation of your horizontal asymptote. If you'd like, you can even take your functions and put them in your calculator to analyze it, to look at the equation of your horizontal asymptote and compare from there. So I have the first 2 parts filled in, and I want to talk a little bit about the comparison between these two and label these in terms of balanced, bottom heavy, and top heavy, which I'll define in a few minutes. So I want to look specifically at the degrees of my numerator and denominator. So notice how in number 1 and in number 3, the degrees of the numerator leading term and the denominator leading term are the same. So that's what we call a balanced function. For number 2, the degree of the denominator is larger than the degree of the numerator. So that's what we call bottom heavy. That's also the case in number 4. The degree of my denominator is larger than the degree of my numerator. And then lastly, Number 5, the degree of my numerator is bigger than the degree of my denominator, so that's what we call top-heavy. And the way to determine your horizontal asymptote will be based on these 3 categories. We'll formalize the notes as soon as we get through the chart. But if your degree is balanced, or if your function is balanced, so like in number 1 and number 3, where the degrees are equal, you are going to take the ratio of your leading terms. So you're going to simplify. I have 5x squared over x squared. That reduces to 5. So the equation of my horizontal asymptote is y equals 5. In number 3, it would be 8x squared over 4x squared. I'm going to simplify that to 2, and my horizontal asymptote is going to be y equals 2. When your function is bottom heavy, your horizontal asymptote is going to be y equals 0. And when your function is top heavy, there's going to be no horizontal asymptote. There's actually going to be a slant asymptote, which we'll talk about in the future. But for right now, you're going to recognize that a top heavy function, like we have in number 5, is going to be no horizontal asymptote. So simplifying the other 3 here is not going to help us with the equation of our asymptote, but it's going to give us our long run behavior, which we'll talk more about as well. But for right now, you just might want to have it in mind that this would be 3x over x squared, which would give me 3 over x. This would be x squared over x cubed, which would be 1 over x. And this would be x squared over x. That's going to help us with our long run and our slant, which will be x. So we talked a lot about different things. Let's formalize those notes. So our method for finding horizontal asymptotes is to compare the degree of the expression in the numerator and the expression in the denominator and follow our rules. So we said that when it was balanced, because that was the one that we started with, I'll color coordinate them, my balanced functions, you find the ratio of the leading terms. When my function was bottom heavy, our equation was y equals 0. And when our function was top heavy, there was none. And we're going to talk about slant asymptotes in the future. So those are your notes on horizontal and vertical asymptotes. So there are some practice questions where you're going to identify top heavy, bottom heavy, and balanced, and there are some where you're going to find the vertical and horizontal asymptotes. So give those all a try, refer back to the video if you need to, make sure you have all these rules down so you're ready to go when we sketch these more complicated rational functions.